Welcome to the first module of our IT security analysis series. And this module is all about network security architecture. So, as you all know, in IT security analysis, we're going to um, determine all the security controls on different layers of the IT infrastructure. That's why we need to understand the network security architecture. Okay, so, I'm Justin Pineda, and let's start. So we start with the layer design, comparing OSI versus TCP/IP. So because this is just a review, there's an assumption that you already know the network fundamentals like the OSI um, model and the layers and the protocols that are running in these layers. But just to give you an idea, Um, so for OSI, so each layer performs a specific function, okay, and the complexity of that functionality is contained within each layer. So the changes in one layer do not directly affect another. So another key feature of the OSI, because TCP/IP is also called the Department of Defense model, uh, because it came first and it's pretty straightforward if you look at the layers. But comparing it with OSI, it's called the reference model. Okay, because if another vendor would create its own protocol, it will just follow the rules and the standards on that layer, and it will be able to communicate with all other network devices. Okay, so for that's why we are using OSI for majority of our analysis, our study. So some of the mnemonics include please do not tell salespeople anything, and then there are others. Okay, but primarily, okay, we start from the topmost, the application, presentation session, transport network, data link, and physical. But during diagnosis, okay, we always start with the physical going up. Okay. So, just to give you a summary, application layer, layer 7 is the actual interface with the computer application. So, the user will be seeing graphics, will be seeing text that is already translated, from bits and bytes, okay, and pulses from physical. Okay. Presentation, so it presents data to the application in a comprehensible way, such as data conversion. So when we talk about compression, decompression, formatting, we refer to the presentation layer. Okay. Next would be session. So it manages session which provide maintenance on connection, such as if the connection is idle, active, inactive. Okay. So that's session. So these three in the TCP/IP will fall under application. Okay. And then yeah. So for the transport, it handles the packet sequencing, the flow control. Okay. So when we talk about port numbers, we talk about transport layer. Okay. So in TCP/IP model, there's also um, a, a a transport layer counterpart. And then we move to the network. So describes routing, moving data from a system on one LAN to a system on another. Okay. So when we talk about IP addresses, we talk about the network layer. Okay. And then for data link, it handles access to the physical as well as local area network communication. So this is the layer that has connection to both um, hardware and software. Right? So there's a logical link control, um, which interfaces with the software, or which interfaces with the software, and the MAC, okay, or the media access control, which interfaces with the hardware. And then obviously, um, layer 1 is physical, describes units of data such as bits, okay, represented by pulses. It can be electric signals. Um, yeah, so that would be the short summary of the OSI layers. Some of the network access and transport layer protocols and concepts would include MAC address, because we're going to analyze um, MAC address and IP addresses and its behavior, okay, its traffic. So MAC address is a unique hardware address of an Ethernet network interface card, or the NIC. Although in newer books, they they do not classify MAC address as unique anymore because it can be easily spoofed. So there are other things that are checked aside from the MAC address. Okay, but just for definition's sake, we say that it's a unique hardware address of an Ethernet network interface card. And then we move to IPv4. Okay, so it's the fundamental protocol of the Internet, designed in the 1970s to support packet switch networking. It's a simple protocol designed to carry data across the network. So it's a 32-bit, okay, 4 octets in format. So um, this is the form. Okay, so the version. If you study the CCNA, you follow the CCNA curriculum, they will deal one chapter just for the IPv4. Okay, and then we have RFC 1918 addresses. So RFC is request for comments. So these are standards that um, and it's like the man page in networking. So it provides all the specifications of a specific protocol, okay, or a specific network concept. Now for RFC 1918, um, it talks about private IPv4 addresses, which is not routable outside. So it's only used internally. So private IPv4 addresses which may be used for internal traffic that does not route via the internet. Okay? And then we also have NAT. Okay? Because when you analyze later on logs, some traffic may be, some IPs may be NATed. Okay? So this is used to translate IP addresses. Initially, the goal was to preserve external IP addresses. Okay? So it is frequently used to translate RFC 1918 addresses as they pass from intranets to the internet. So there are different types of NAT. We have static, which is one-to-one translation between addresses. We have dynamic, which reserves a number of public IP addresses in a pool. And then PAT, or port address translation, makes a many-to-one translation from multiple private addresses to one public IP address. So later on, when we design our security operations, so this is one of the things that we have to consider. Are we going to use PAT? Because when you use PAT, this is very dynamic, and it's hard for you to do your tracking or your security analysis later on. And then we also have ARP, or Address Resolution Protocol. You use to translate between layer 2 MAC addresses and layer 3 IP addresses. So you can do that in your command prompt to check the pairing of the IP and the MAC addresses. And then we have TCP, which is a layer 4 or transport layer protocol, uses a three-way handshake, okay, SYN, ACK, and ACK, to establish connection first between the source and destination. We know this. Okay. ICMP, layer 3 protocol, use troubleshoot and report error conditions. So some of the applications would be ping, which is sending ICMP echo request to a node and listens for an ICMP echo reply. And then trace route, which uses an ICMP time exceeded messages to trace a network route. So these protocols are very important, especially because um, these protocols are used to check whether a system is alive or not, okay, and to check whether there is a firewall in between. Next would be UDP, or User Datagram Protocol. So it's a simpler, faster cousin to TCP. UDP has no handshake, session, or reliability. So it's faster. It's unreliable in Cisco sense because it just sends, it does not do um, handshakes. And if it reaches, then it's good. If it does not reach, then it will send again. So that's how UDP works. And then some other protocols. We have Telnet, which uses port 23. It's used to do remote access to your servers, but it's weak because it provides no confidentiality. Meaning, when it passes through, the network, and you run a sniffer, then you'll be able to see it in clear text. FTP, File Transfer Protocol, is used to transfer files, okay, to and from servers. So it has no confidentiality or integrity whatsoever. So it uses port 20 and 21. Okay. So although these are more substandard or below standard protocols, we still have to know them because when you do your analysis, at times you will see traffic on port 23 or on port 21. So you will have to investigate why they are using it. We also have TFTP. It runs on UDP port 69, provides a simpler way to understand files, and is often used for saving router configurations or bootstrapping via a network by diskless workstations. And then we have SSH. So this is now the standard. Using SSH, okay, it is a secure replacement for Telnet. Okay, FTP and the Unix are commands. And then for mail, we have SMTP and POP3. So SMTP is used to transfer email between servers. It uses TCP port 25. For POP3, it's used for client server email access. It uses port 110. IMAP is using port 143. For DNS, okay, um, it uses port 53. It's a distributed global hierarchical database that translates names to IP addresses and vice versa. So instead of typing the IP address of a particular destination, because that's what the routers would do, it will route the packet to the IP address. So there's a translator so that the user will not be typing the IP. So it will type words using letters and numbers, combination of both. And it's the job of the DNS to translate this to the IP address. So DNSSEC provides authentication and integrity to DNS responses by the use of public key encryption. And here are some other protocols. We have SNMP, used to monitor network devices. So it provides logs, it provides status using port 161. We have HTTP and HTTPS. So HTTP used to transfer unencrypted web-based data. This uses port 80. HTTPS transfers web-based data via SSL or TLS on port 443. And then we have Bootstrap, which is used for bootstrapping via a network of diskless systems. And we also have the HCP. So the HCP allows more configuration options as well as assigning temporary IP address leases to systems. So the DHCP will, if set up in a local network, it will give IP addresses or lease IP addresses to network devices to the network, so it can communicate internally or going outside to the internet. Okay. LAN physical network topologies, we have bus, okay, tree and ring. So for bus, it connects network nodes in a string. So this is an example of a bus. And we also have a tree, a network with a root node, okay, and the branch nodes are at least 3 levels deep. And the ring connects network nodes in a ring. If you follow the cable from node to node, you will finish where you began. So this is the ring. Okay. And then star is the dominant physical topology for LANs. Each node is connected directly to a central device, like this, okay, such as a hub or a switch. And then mesh interconnects network nodes to each other. So here is an example of mesh. Now let's go to network devices and protocols. So when we say repeater, okay, it's a network repeater. It's a layer 1 device. So it receives bits. So when we say layer 1 device, layer 1 is physical layer. Okay, so it receives bits on one port and repeats them out the other port. In no understanding of protocols, it simply repeats bits. So it's not as intelligent as our network devices now. Okay, so that's why it's called layer 1 device. A hub is a repeater with more than 2 ports. So it means repeater is equal to hub. Okay, provides no traffic isolation and have no security. Okay. So once you tap in your sniffer, your Wireshark, it can sniff all the traffic that passes through the repeater or hub. A bridge is a layer 2 device. It has 2 ports and connects network segments together. Has 2 collision domains. It learns the MAC address of nodes on either side. Um, so layer 2, meaning it can communicate, it can understand MAC addresses. So, so collision domains, it means these devices can send simultaneously at a given time. And then we have switch. It's a bridge with more than 2 ports. It provides traffic isolation by associating the MAC address of each computer and server with its port. So at times we can lock the specific port or Ethernet and assign it to the particular MAC address. So only that computer can access that port. Okay. Other concepts, virtual LAN, group of devices on one or more LANs or local area networks that are configured to communicate as if they were attached to the same wire. Okay. When in fact they are located on a number of different LAN segments. So this is important for, well, um, separating the broadcast of the networks, okay, even if physically they are not in the same room. Okay. At the same time, security, because you can contain the grouping based on category or based on department. Like for example, here we have engineering, which is visible on all floors, first floor, second floor, and third floor. But they are able to group them in one VLAN. Same with marketing, same with accounting. I'm not promoting Cisco router. This is a sample, sample topology. And then we have span ports, okay, and top or test access ports. So when we say span ports or port mirroring, this allows you to take a copy of network traffic as it passes through a network switch. So again, because it has a collision domain per interface, once you tap and run a sniffer, you won't be able to sniff other traffic aside from yourself. So you would like to be able to sniff all the traffic, okay? Especially if you use your security tools like intrusion detection system. So you're going to use a span port. So you use it to send a copy of network packets in on one switch port or an entire VLAN to another switch port. Okay. Another way is to use tap. So it provides a way to tap into network traffic and see all unicast streams on a network. Okay. So this is a preferred way to provide promiscuous network access to a sniffer or network intrusion detection system. Okay. And then it can fail open. Okay, so that the network traffic will pass in the event of a failure, okay, which is not true for hubs or switch span ports. So at times when the device fails, you would like, if when we say fail open, all the devices can still access to the internet. Okay, because if it's in line, if it goes down, then everything will go down. So nobody can access going out or going in. Routers. These are layer 3 devices that route traffic from one LAN to another. Okay, so IP-based routers make routing decisions based on source and destination IP addresses. So there are different routing protocols. We have RIP, we have RIP version 2, we have BIGRP, OSPF, okay. And we also have firewalls. So they filter traffic between networks. In some books, they define firewalls as a device that enforces a policy. Okay, so TCP/IP packet filter and stateful firewalls make decisions based on layers 3 and 4. Okay, while proxy firewalls can also make decisions based on layers 5 to 7. So it again, the positioning of these types of firewalls depend on the architecture that you are planning to do. Okay. So we start with the packet filter firewall. So it's the simplest and fast firewall. There's no concept of state. Each filtering decision must be made on the basis of a single packet. So no way to refer to past packets to make current decisions. So stateful firewalls. So for packet filter, it just checks the IP and the protocol, and that's it. If it says allow, then it will allow. If there's no rule, it will not allow because of implicit deny. And then we have stateful firewalls. They have a state table that allows the firewall to compare current packets to previous ones. They are slower than packet filters, but more secured. So more features. Again, if it's more secured, probably less functional or less usable. So it becomes slower, but more secured. And then we have proxy, okay, firewalls that act as intermediary servers. And both packet filter and stateful firewalls pass through or deny it. They are another hop along the route. So yeah. There are different techniques to detect whether you have reached the proxy or not. And then upon reaching the proxy, you can also check if you can pass through based on the policies that they have implemented. And then we have application layer. Proxy firewalls. These are firewalls that operate to layer 7. So imagine the filtering, um, but this is way slower because it takes a lot of layers in the OSI. So it must understand the protocol that is proxied. So dedicated proxies are often required for each protocol. And then we also have circuit level proxies which operate at layer 5 or the session layer and are lower down the stack than application layer proxies, which works at layer 7. So it allows circuit level proxies to filter more protocols. No need to understand each protocol, and application layer data is simply passed along. So there are still variations of proxies. So there are proxies that work up to session. There are proxies that work up to the application layer. Now, some of the fundamental firewall designs. So the first one is bastion host. So it's any host placed on the internet which is not protected by another device. Okay. So it must protect themselves and be hardened to withstand attack. That's the bastion host. Okay, and then we have the dual home host. It has two interfaces, one connected to the trusted network. The trusted network is usually the corporate network, and the other connected to an untrusted network such as the internet. Okay. So a user wishing to access the trusted network from the internet would log into the dual home first and then access the trusted network from there. So um, there is a pass-through first, okay, or a checkpoint, which is the dual home. Screen host architecture is an older flat network design using one router to filter external traffic to and from a bastion host via an access control list. Okay. The bastion host can reach other internal resources, but a router ACL forbids direct internal-external connectivity. So again, what they're doing here is a um, defense in-depth type. So you cannot directly access the trusted zone. It has to pass through a checkpoint. Okay? So that if there are attacks or if there are suspicious traffic, it will have to pass through um, a gate, and then if if it spreads there, then fine, it can be cut off or a response can be done, okay, without directly infecting or affecting um, the systems or the assets in the trusted zone. And then we also have a demilitarized zone. So it's a screen subnet dual firewall design. We have two firewall screen, the DMZ, the subnet, or a three-legged DMZ, wherein there's a single firewall DMZ. So we'll explore that more further on the design. But for the demilitarized zone, there's always um, a network going out to the untrusted zone, um, an interface or a network to the DMZ where the servers are located, and another network or interface located to house the trusted zone. Okay. Some other uh, technologies that we will be using, okay, include the IDS and IPS. So IDS, or intrusion detection systems, are detective devices designed to detect malicious, including policy violating actions. And usually it's a combination. An IPS is combined. This is a preventive device designed to prevent malicious actions. So usually these devices are placed after the firewall. So whatever traffic that passes through the firewall will also be screened. Okay. So types include network-based and host-based. So network-based meaning it's placed as a sensor. So as it passes through going out, going in, or east-west traffic, it, lateral movement will be detected. Or host-based, meaning there's a software installed in the server or the end device to monitor the traffic. So what are the features? Okay, so there's pattern matching. So works by comparing events to static signatures. So there's a signature base similar to anti-malware. Okay. Protocol behavior models the way protocol should work, often by analyzing RFCs. So for example, if the normal behavior is seen act, that's the three-way handshake, and then the IDS detects a different behavior like seen act, seen, so it doesn't complete the three-way handshake, it will flag as a problem with the protocol behavior. Okay. And last would be anomaly detection. So it works by establishing a baseline of normal traffic and reports traffic that fails to meet the baseline. For example, it can be voluminous traffic at 10 p.m. Okay? So they will flag it as anomalous if they find some number of traffic, a large amount of traffic, because there should be no traffic during that time. Everybody is at home. So something like that. That would be an anomaly detection. And then last would be honeypots. So honeypot is a system designed to attract attackers. So it's a decoy. It's a decoy machine, a decoy network. So um, attackers would attempt to attack the honeypot, knowing at the back of their minds that they are actually attacking the real target. So all the traffic, all the attackers' traffic will be diverted there. HoneyNet, real or simulated, these are network of honeypots. And then there's also low and high interaction honeypots. So low interaction honeypots simulate systems or portion of systems, usually by scripting network actions, such as simulating network services by displaying banners. Okay, so these are what we call low interaction honeypots. And we have high interaction honeypots, which run actual operating systems in hardware or virtualized. So implementing honeypots is actually tricky because it also involves investment. Investment, time, because you have to monitor it, you have to update it as well, you have to check, and once you got attacked, you still have to fix it, do some remediation and all. So we will discuss more of these technologies in the next modules. Okay, so that sums up the network security architecture module. So I know this is a crash course of the network or a review of the network fundamentals, but these are very important topics coming from the type of networks and the types of devices and the important protocols and um, the firewall architecture and other devices like IDS, honeypots, and other controls that we will be putting in place. So these concepts are very important to be familiarized with because we will be using this throughout the other modules. So if you have any questions, you may leave it in the comment section or you can email me at justinp@pinetacybersecurity.com. Okay, thank you very much and see you in the next module.